In this video, I'm going to show you how we can index a powder pattern by hand and then calculate the lattice parameters. We're going to do this for an unknown material. Let's imagine you've been given a small chunk of shiny metal and your supervisor doesn't quite remember what it is. They think it's probably either tantalum or tungsten. Tantalum and tungsten both have very similar space group, IM bar 3M, both body-centered cubic, and the lattice parameters are quite similar as well. 3.3 angstroms for tantalum and around 3.15 angstroms for tungsten. So how are you going to tell what this metal is? Well, the one thing you can do, obviously, is do some XRD on it. So you get an X-ray diffraction pattern, and it looks like this, a very nice pattern. Looks almost like someone simulated it in crystal diffract. But that doesn't actually solve your problem. Now you have a shiny piece of metal and a diffraction pattern. Let's imagine that you are not able to use the databases or any specific diffraction software to solve this problem. You're going to have to solve this issue the old-fashioned way. From the diffraction pattern, we could see that the peaks are spaced fairly evenly. This indicates that the sample probably does have cubic symmetry after all. So we can create a peak list quite easily. As you can see here in the table that we've got our 7 peaks from the diffraction profile, and we've listed the peak position into theta and the relative intensity. What's important is that as we go through this exercise, you'll notice I don't refer to the relative intensity at all. Everything we're going to do is purely from the peak position. So what we're going to do is we're going to use a method called the sine squared theta method. This will help us to work out likely indexing or Miller indices for the peaks that we've observed. The advantage of this method is that we don't need to know the lattice parameter, and we don't need to use any software, just a calculator. I use Microsoft Excel though, it makes it a bit easier. So we need to combine 2 equations. First of all, let's consider Bragg's law. N lambda equals 2d sine theta. We can rearrange this to give us sine theta equals n lambda over 2d, and then square all of that to give us sine squared theta equals n squared lambda squared over 4d squared. We can also consider the equation that correlates the d-spacings between planes in a lattice and the unit cell size for a cubic system, for example. 1 over d squared equals h squared plus k squared plus l squared all over a squared. Combining these 2 equations gives us sine squared theta equals n squared lambda squared over 4a squared multiplied by h squared plus k squared plus l squared. This n lambda section effectively becomes a constant, and so we can ignore that for the time being. So what you can see is there's a direct correlation between the position of the peaks in sine squared theta with the Miller indices h, k, l. Some other useful things that we can define. Let's have make a new parameter m, and m is just going to be the sum of h squared plus k squared plus l squared. You'll notice that it's not possible to find values for certain combinations of h, k, and l that will give the particular values 7, 15, 23, 28. So if you have a 1, 0, 0, m would be 1, a 2, 0, 0, m would be 4. It's not possible to get a combination of h, k, and l that will give you n equals 7, for example. And this will be particularly important in a short while. The other thing to mention is that if you're going to do this in Excel, you need to convert your angular positions into radians, and you can do that by the equation on the screen here. So the first thing, we're going to do the sine squared theta method. This is the table that we need to fill in to do this. The ultimate objective is to fill in the m column on the right hand side, and from that we can calculate the HKL values. So I've filled in here 2 columns already. We've got the peak positions in 2 theta. I've then filled in the theta position in radians. To get from 2 theta to the theta in radians, we have to first divide the 2 theta values by 2 to give theta, and then convert them to radians using the equation we saw a minute ago. So for example, the peak at 38.46 becomes theta of 0.3356 in radians. The next step is then just to simply take the sine of that theta in radians. So sine theta for our peak at 38.46 becomes 0.3294, and so on. We can then also square those values, so just multiply 0.3294 by itself, and that will give us a sine squared theta value of 0.1085. So that's our sine squared theta value for peak 1, and so on. We then take the ratio of all the sine squared theta values compared against the first peak. Actually, you can pick any peak, but I tend to always work from peak 1. That means that in the first peak, we're going to take the ratio 0.1085 divided by 0.1085, and we'll multiply that by an integer number, a whole number. So we'll start in ratio 1 by multiplying all the values by 1. So 0.1085 divided by 0.1085 multiplied by 1 gives us 1. 0.2171 for the second peak divided by 0.1085 multiplied by 1 gives us 2, and so on. And so we can fill in the whole column. What you will notice, however, is that we have a value here of 7. Now these ratios are possible values for m, and we know that we cannot have an m value of 7, and so that means that this is not a possible solution for m. If we go to ratio 2, what we're doing here is instead of multiplying by 1, we're multiplying by 2, and so on. And we could carry on, we could multiply by 3, by 4, by 5, whatever was necessary until we find an appropriate answer. And what you can see here is that these values are all pretty close to integer numbers, which is good. We don't want, say, 1.5, 3.5, numbers that don't look like integers. So we can round all these up quite easily, and they're all permitted values. 2, 4, 6, 8, 10, 12, 14 are all fine. So these are possible m values. So we can fill in that m column. So we have m equals 2 for the first peak, 4 for the second peak, and so on. What you can notice from this is that h plus k plus l, which is effectively our m value, they're all even numbers. So if they're all even values for m, that means that what we're looking at is a body-centered lattice. There are other rules for different types of lattices, but in this case it's a body-centered lattice, which fits with what we were expecting. So we can convert these m values to hkl values now. Once you get to larger m values, there can be multiple possibilities, but for small values there tends to only be one solution. So for example, 110 reflection, 1 squared plus 1 squared plus 0 squared equals 2. So m equals 2 is 110 reflection. For m equals 4, that must be a 200 type reflection. 2 squared plus 0 squared plus 0 squared equals 4. And so on. So we get possible Miller indices for all of our 7 peaks. As I say, once you get up to the higher m values, there may be other possible solutions. But these are reasonable values in this case. So what we've done here is we've indexed our diffraction pattern. All we've done is use Excel and a little bit of logic and maths, and it's been pretty straightforward. And so you can see here our pattern from our metal sample overlaid with the HKL values for the individual reflections. Just to step aside from this particular mysterious sample for a second, we can also do this routine for non-cubic samples, but it is a lot harder, and it gets harder very quickly. There are ways to do it. You can see some, for example, in Klug and Alexander in chapter 6, but this is where really, if you're looking at a non-cubic system, you really are going to probably be better off using software like Index and Refine and WinXPow. But bear in mind, if you're using these kind of automated indexing programs, they don't have any intelligence. They're just kind of find numbers that work, not necessarily the best answer. You must always check the output. Does it make sense? Does it follow the rules? Does it answer the problem that you're looking at? So we've got now our peak positions, and we've got our Miller indices for this mysterious metal. We looked at this equation earlier on briefly. 1 over d squared equals h squared plus k squared plus l squared over a squared. We can use this equation to manually calculate the lattice parameters A for our unknown powder pattern. First of all, we need to rearrange the equation for A. So it becomes a squared equals d squared times h squared plus k squared plus l squared. We also need to then convert our peak positions from 2 theta into d spacing. This is done by a simple rearrangement of Bragg's law. Again, in the spreadsheet that I'll attach with this, you can see how I've done that in Excel. So our peak at 38.46 degrees 2 theta has a d spacing at 2.339 angstroms, and so on. So we've got a list now of our peak positions in d spacing. Next, we can compare this. So we've got our d spacings and our Miller indices for the peaks. And this is all the information that we need to calculate the lattice parameters. We can pick out any peak and use the equation that we derived a second ago to work out the lattice parameters. So for example, for a 110 reflection, we found this at d spacing at 2.339 angstroms, and that was our 110, so we can plug those values into the equation there, and that gives us lattice parameter A of 3.308 angstroms. If you remember the possible values we were given earlier, we can now confirm that our mysterious metal sample is in fact tantalum. The equation for a tetragonal system is a little bit more complicated. 1 over d squared equals h squared plus k squared plus l over a squared plus l squared over c squared. So we have a separation here of the h, k, and then the l Miller indices. So if we want to work out the lattice parameters from this, we're going to need an HK0 type reflection to give A, and a 00L reflection to give C. So for example, you might look for a 001 to find out what C is, and then a 110 to find your A lattice parameter. The equations are shown here for orthorhombic and hexagonal systems. Working out the lattice parameters manually for these is still very simple. Once you've indexed the pattern, it's very easy to do. Once you go to lower symmetry systems, it gets a lot more complicated very quickly. And so in these instances, yes, you probably still want to use software. But hopefully this video has given you a good idea of how you can manually work out the lattice parameters and index powder diffraction patterns for simple systems.